There was one phenomena in quantum physics that troubled Albert Einstein more than any other. A feature of theory he eventually referred to with equal parts of frustration and fascination as spooky action at a distance. Today, we call it quantum entanglement, and it forms one of the central pillars of quantum computing. Why quantum is so weird and why you will love it. Welcome to my lecture series, Learning Quantum Computing from Zero to Hero. I am Professor Janki Vimani, and on the day-to-day basis, I help invested stakeholders make the most out of their resources by inventing novel solutions using emerging technologies, from modern storage systems to quantum computing and machine learning, all while tackling the real-world challenges of real system deployment. Basically, I live at the intersection of science, creativity, and practicality. Now, let's talk about something really fun, quantum. So, what is this entanglement that worried Einstein so much and it was so tough for him to accept that? Entanglement is a remarkable situation in which two particles become so deeply connected that they must be described as a single quantum system, no matter how far apart they are in the space. When you measure or alter one particle, the other responds immediately, even across enormous distance. They can be in the same room or they can be as far as like galaxies apart. So for example, if two entangled particles must always sum to a spin of 0, then adjusting the spin of 1 will cause the other adjust instantaneously, preserving the total. This happens whether they are separated by centimeters or light years. And this happens instantaneously, even faster than the speed of light itself. Einstein resisted this idea because it appeared to violate the speed of light limit embedded in classical causality. It seemed to allow a kind of instantaneous connection that defied his intuition about how information should propagate through space. Yet, through the decades of increasingly precise experiments, entanglement has been confirmed as a genuine feature of physical world. And instead of resisting it, modern quantum engineering embraces it. Do you happen to know a person whose answer to everything you ask them is maybe? Well, maybe is a superpower for quantum computers. More technically, we call it as a power of superposition. To understand quantum computing, we need a second key concept, that is superposition. A classical bit is either 0 or 1. A qubit, by contrast, can exist in superposition of 0 and 1 simultaneously. It behaves not as a single defined state, but as a wave of probability amplitudes. When multiple qubits are linked through entanglement, we no longer treat them as an isolated unit of information. Rather, they form a collective quantum state that can represent an exponentially large computational space. For certain algorithms, this leads to a dramatic computational advantage over classical machines. Where are we today and how far have we advanced in the world of quantum systems? Even a decade ago, we could reliably entangle only a few dozen qubits at a time. Today, landscape is very different. In 2025, which is this year, Caltech demonstrated a 6,100 qubit neutral atom array, the largest programmable quantum array to the date, with coherence time on the order of 13 seconds and individual qubit control fidelities around 99.98. If terms like coherence is new to you, hold on, I'll be covering that soon in this lecture. On top of that, companies like IBM have released a roadmap towards fault-tolerant quantum computing. Now, why fault tolerance is important? Because today the biggest problem of quantum computers is the noise, and we will be covering that in our upcoming lectures. So don't worry, you will learn what noise is and why noise is a big problem in quantum computers. But companies like IBM have launched a roadmap of fault-tolerant quantum computing. That means quantum computing that can handle noise internally, and to user we don't have to worry about the noise of this computations. With a planned system, Starling, targeting 200 logical qubits supported by advanced quantum error correcting codes. So now in order to support 200 logical qubits that are fault tolerant, physically many more qubits would be utilized in order to design such a system. Thus, this is a large-scale advancement at core. These developments indicate not just increase in scale, but genuine progress towards usable quantum computation. What is coherence, and how property of coherence is different from property of entanglement? Before going further, it is essential to clarify two foundational ideas that often are confused. Quantum coherence is a property of an individual qubit. It refers to how long a qubit can maintain a stable quantum phase and therefore remain in superposition. Coherence time determines how long meaningful quantum computation can occur before the state collapses. On the other hand, quantum entanglement, as we already learned earlier, is a property of multiple qubits. It describes the non-classical correlations between them. Entanglement enables qubits to act as a unified computational system. Relationship between the two is that coherence is required to maintain entanglement. When coherence is lost, entanglement collapses as well. Thus, coherence is the resource that makes entanglement useful for computation. This distinction becomes critical as we discuss the greatest engineering challenges in the field. So remember the difference between coherence and entanglement. Now, if coherence is a thing, quite natural, decoherence can also be possible. And what is decoherence to the world of quantum? Every quantum computation depends on preserving coherence long enough to reliably manipulate entangled qubits. However, quantum states are extraordinarily sensitive to their environments. Things like thermal noise, electromagnetic interference, imperfect control, unwanted interaction with nearby particles, any such things can disturb the coherence, can cause decoherence. And hence, a decoherence would collapse the superposition and destroy the entanglement. This is the central challenge of quantum computer design. And it is why adding even one additional error-corrected, well-behaved qubit is a significant scientific advancement. As researchers continue expanding entangled systems from dozens to hundreds to thousands of qubits, we approach machines capable of solving computational problems that classical computers cannot feasibly address. Quantum computing is no longer theoretical speculation. It is rapidly becoming an engineering discipline, one that depends on your understanding of superposition, entanglement, coherence, and decoherence. Four key concepts at the heart of quantum computing. And if you have followed this far, excellent. You now have the foundational vocabulary required to understand how modern quantum computers operate and what challenges still remain. Next, we will look into what are the biggest advancements that can be achieved using this technology of quantum computing.